And now Peter Lemke from the Alfred Wegener Institute, perhaps more importantly, is also the chair of the IIASA Council. Peter.
Well, ladies and gentlemen, there should be a slide deck here. What I would like to talk about is the global challenges, and well, it's back. And they, of course, arise from the deficiencies of our understanding of the Earth system, made up of three components, and I just divided it into three, which is the climate system, the ecosystem, and the human system. They are all linked together, and the level of our understanding is quite different in those three areas. And this will be mainly my takeaway message from here. And of course, the difference in the understanding gives the rise for the great challenges. So I would like to start with a wider view, going back even further than Simon has started with 200 years ago. And 200 years ago, in the golden age of classical mechanics, it was understood that, at least assumed, that the universe in principle is predictable. So you only had to know the initial conditions, the state vector of all creatures in the universe, of all items of the universe, and you had to know all the forces that act on these items. So you had to know the system dynamics. And then the future was just the integration of differential equations. And I think this is what Laplace's demon was about, and he thought that in principle this was possible. Of course, we know today this is not possible because the system is complex, has interactions and feedbacks, has internal nonlinear dynamics, deterministic chaos, has many temporal and spatial scales involved, has inadequate external forcing and initial conditions, and of course computer limitations will always give us a very, very coarse answer. So the question is, of course, what can we really do with the system if we can't predict, and how predictable is the system at all? Now let's look at the first component of the Earth system, which is the climate system. It is made up of several components with far different timescales: atmosphere a few days, ocean 100 years, the ice, and if you look at the ice sheets, 100,000 years, biosphere. All are intimately coupled, and these are forced by the sun and by men. And on longer timescales also geological forces are interesting, but that's not the discussion point here. Now the interaction between the different components here are regulated by the exchange of heat, momentum and matter. And for those interactions we do have conservation equations, well-proven laws of physics, conservation equations for energy, for momentum, and for matter. And even in this simple system, the prediction is not possible beyond a few days, and this is the weather forecast. If you want to go for longer time scales, you have to do prediction in the statistical sense. So what you do is you just make an ensemble of different simulations, and then you calculate the mean and the variance of the system, and you get the mean development. Examples are, for instance, forecasts for El Nino, and you may have also heard about that. We are now trying to start decadal forecasts with very limited success so far. So our understanding of this system is quite good, but the ecosystem is, we are less well developed. Although this system is much more complex, there was an impressive evolution of the modeling and understanding of climate, chemistry, and ecosystems for the long-term climate response, mostly involving the carbon cycle and other chemical species. And this coupled system is now the basis of the last, the fifth IPCC assessment report, and the understanding of the ecosystem, for instance, is only partial. It's only that part that is really important for the carbon cycle. So much of the ecosystems we don't understand, and for the human system, this is even more problematic. We don't have much data on this. So in my last slide, I would like to dwell a bit on what, in these three areas, what is the level of understanding. And now if we look on the left-hand column here, this is the requirement for a prediction system in the sense of climate. So you have to monitor the relevant variables to get a long-term data set. You look at process studies to understand physics that you don't resolve in your models, like a cloud system, for instance. You do system analysis to understand the system dynamics, and finally, you do data assimilation and you develop a prediction system like they do it in the weather and the climate forecast systems. Now, I put here under climate system green pluses. So 2 green pluses would be the perfect model. So we are not perfect yet. There are lots of things that we don't know. But if you look at the ecosystem, the pluses are yellow, which means that there's a lot to do. Data sets are less available. Process studies are not all known. And system analysis is done. But there is, of course, a question of system dynamics. And there is, of course, a big question. The red question mark here says that we are far away from data assimilation and prediction systems in this sense. Now, the human system has less data on, even sometimes we are still looking which ones are the relevant variables, so long data sets are not available. And process studies are being done. For instance, for the population, we have heard many examples here for process studies. System analysis is done, but there's still a big question mark on how to understand the system dynamics in order to project its future. And I think this is the basic, my basic message is that this is where IIASA actually comes into play, to look at the system analysis of these different systems, trying to find out the dynamics that's ruling them, but more so looking at the interactions between the different systems. So this ellipsoid should actually include more than, should also include the climate system party, which does it only partially. But this interlinkages between the three different parts, that's the main part that I think IIASA should do. So with this, I would like to end.